Hello Calc 3, welcome back to another video. So in this video we'll be covering the first half of section 16.4, which is the last section that we will cover in this course, so hopefully that makes you happy. The topic for the video today is circulation density and flux density, and we'll start out with the concept of circulation density. You can think about it intuitively as how much a fluid is spinning around some axis coming out of the plane. And we will also see that this is really just the k component of the curl vector field that would be covered in section 16.7 if we were to cover section 16.7. So suppose that f equals m of xyi plus n of xyj is some velocity field of a fluid that's flowing in the plane, and that the partial derivatives of the component functions m and n are all continuous over some region R, then we can let xy be some arbitrary point inside of that region R. As I've drawn in the diagram here, you can see I have a green region R, and then inside of that region we have our red point xy. And we can let A be a small rectangle that's completely contained inside of the region R, with one of the corners at xy. So in this case, we made the bottom left corner at xy for our rectangle A there. And again, we have to assume that the partial derivatives of the component functions m and n do not change signs anywhere inside of this rectangle A. So as long as we make our rectangle A small enough, we can probably make that the case. And then the circulation rate of our vector field f around the boundary of this rectangle A will be the sum of the flow rates along each of the sides of A in the counterclockwise direction. So you can see in the diagram here that we are considering flowing around this purple rectangle A in the counterclockwise direction. And also note that the length of our rectangle is delta x and the height of our rectangle is delta y. So again, if we want the circulation rate of our vector field f around the entire boundary of our rectangle, it suffices to take the sum of the flow rates along each of the sides of the rectangle. So we'll have 4 different expressions here for each of the sides, and we'll sum them together to get the circulation rate around the entire rectangle A. Okay, so here are the 4 different flow rates that we get for the top, bottom, right, and left sides of our rectangle A. So for the top of the rectangle, the flow rate is going to be approximated by big F of x, y plus delta y dot minus I times delta x. And the intuition here, so as we're on the top of the boundary of our rectangle A here, we're moving in the direction minus I because we're moving exactly to the left in the negative x direction. And that's why this dot minus I is showing up here. And this f of x, y plus delta y is this other red point up here. There we go. So I can draw an arrow there. That's the point that we are evaluating the vector field at. So we're getting the velocity vector of the fluid at that particular point, and we're finding the scalar component of that velocity vector in the direction of minus I, and then we're multiplying by delta x, which is the length of that entire top side of the rectangle, and that'll give us an approximation for the rate of flow of the fluid along that top the top side of our rectangle. And once we write it as f of x, y plus delta y dot minus I delta x, then we can just rewrite that as minus m of x, y plus delta y, because when we take the dot product of f and minus I, we will just get the negative x component, or the negative I component of our vector field f, which will be this minus m of x, y plus delta y. And then of course we still have our delta x coming through at the end, so that'll end up over there. And the expressions for the bottom side, the right side, and the left side are all similarly derived here. So for the bottom, we have f of xy. So we're looking at the point xy this time. Dot I, because on the bottom we're moving directly to the right, times delta x, which is the length of that bottom side. And this will equal m of xy times delta x. For the right side, we have f of x plus delta x y dot j, because this time we're moving exactly upwards in the y direction, times delta y again, which is the length of the right side. And this will just be equal to n of x plus delta x y times delta y. And then finally, the left side can be expressed as, or approximated as, minus n of xy times delta y. So these are expressions for the flow rates along each side of this rectangle, and we can approximate the net circulation rate around the entire boundary of our rectangle A by summing up these 4 different flow rates. So it's kind of instructive to sum them up 2 at a time. So if we sum the top and bottom together, then we end up with negative m of x y plus delta y plus m of xy all times delta x. So that's taking these 2 expressions here and summing them together. And this is approximately minus the partial derivative of m with respect to y times delta x. And the reason is that this minus m of xy plus delta y plus m of xy expression is the numerator of the difference quotient that shows up in the partial derivative. And typically we divide by delta y. So this is that difference quotient multiplied by delta y, which is why we have this partial derivative expression that's popping out there. And if delta y is small enough, then this actually becomes the partial derivative. And again, we'll see that there's a limiting idea that goes on here that eventually gives us the circulation density at a particular point, but we'll get to that in just a little bit. So if we sum the right and left together now, so we take these 2 expressions and sum them together, then we get n of x plus delta xy minus n of xy. And again, we have a similar thing that happens here. So this is the numerator of that difference quotient that shows up in the definition of the partial derivative, but typically we divide by a delta x, and this time we're not dividing by a delta x, so this is approximately the partial derivative of n with respect to x times delta x, and then we still have this delta y that's being carried through on the outside. And now if we take all 4 of, or I guess if we just take these 2 expressions here and we now sum them together, we get an approximation for the total circulation rate, or the net circulation rate around the entire rectangle, which will be approximately the partial derivative of n with respect to x minus the partial derivative of m with respect to y times delta x delta y. So this delta x and delta y, they're still carrying through here. So the circulation density is approximated if we divide the circulation rate around the rectangle by the area of the rectangle. So circulation density is equal to the circulation around the rectangle divided by the area of the rectangle, which again will be approximated by the partial derivative of n with respect to x minus the partial derivative of m with respect to y. And if we let delta x and delta y go to 0, so if we take the limit as the rectangle that has one of the corners at the point xy, if we look at the limit as that rectangle is going to 0, or as the area of that rectangle is going to 0, then we get the circulation density of our vector field f at a particular point xy. So intuitively, the circulation density at a point describes the amount of rotation around the point in the counterclockwise direction. So if you think about looking down on some water, just in the 2-dimensional sense, you're looking down on some water and just the surface, so it's like a plane. And if you look down at this moving fluid, and the fluid is circulating counterclockwise around a point, xy, so you can think like a whirlpool, and it's going in this direction around a point like this. As you get really, really close to that point, then the circulation density at that point is going to be positive. And if you look down and at that particular point, it looks like there's a bunch of water that's rotating around the point in this direction, in the clockwise direction, then the circulation density is going to be negative. So this is the intuition or the interpretation of circulation density. And the value of the circulation density at a point is actually the k component of a more general circulation vector or vector field that's defined in section 16.7. So we won't cover it in the course, but it's a very important vector field called the curl of another vector field. So if you have one vector field, then you can make another vector field called the curl of F. And this circulation density is just the k component of the curl of F. So the circulation density would then be given by curl of F, which is some vector field based off of F, but different. The dot product of the curl of F with just k, the standard unit vector in the z direction, or in the positive z direction. But anyways, this will lead us to our first technical definition here. So the circulation density of a vector field F equals mi plus nj at a point xy is the partial derivative of n with respect to x evaluated at xy minus the partial derivative of m with respect to y evaluated at xy. And again, as I already mentioned, this expression is also called the k component of the curl. So sometimes you'll just see this denoted as curl f dot k, even though we don't know what the curl of f is. But the book does denote it this way sometimes, so just be aware of that notation. And lastly, before we move into the first example, just notice that this circulation density is always going to be a scalar. So when we evaluate the partial derivative of n with respect to x at a point, we get a scalar. And then when we subtract the partial derivative of m with respect to y at the same point, we're still going to be left with a scalar. So the circulation density is a scalar that corresponds to all of the points inside of the region on which f is defined. Okay, so now that we've defined circulation density, we can move on to the one and only example that we have for circulation density here. But I guess it's really more like 4 different examples within one here. So the following represent the velocity of a gas that's flowing in the xy plane, and we want to find the circulation density of each of the vector fields here and interpret the meaning of the result that we get. So I guess I'll just read A, and then I'll go to the solution for A, and then I'll read B and go to the solution for B, and so on. So for A, we have uniform expansion or compression. So this vector field describes a gas that is all expanding from the center or all compressing towards the center. So the vector field is f of xy equals cxi plus cyj, where c is just some constant. So you can think if c is less than 1, then this gas is going to be compressing towards the center. And if c is greater than 1, then the gas is going to be expanding away from the center. And in this case, we have partial n with respect to x minus partial m with respect to y is just equal to 0 minus 0, since the partial derivative of cy with respect to x is going to be 0, and the partial derivative of cx with respect to y is going to be 0. And so the gas is not circulating around any particular points. So the circulation at every point inside of the plane is just 0. Now for B, we have a vector field describing uniform rotation of our gas. So we have f of xy is equal to minus c times yi plus cxj. And it might be helpful to actually show some of these diagrams that I have below as we're going through them. So you can see for A, we have, in this case, c is assumed to be greater than 1. and everything is expanding away from the center here. And in B, we have rotation counterclockwise around the center. So in the case of B, the partial derivative of n with respect to x minus the partial derivative of m with respect to y will equal c minus negative c, which gives us a 2c. So in this case, the circulation density is also constant, the same way that it was in A. But this time we will have rotation at every point as long as c is not equal to 0. So if c is greater than 0, then the circulation is going to be counterclockwise, and if c is less than 0, then the circulation will be clockwise. And again, the circulation at every point will be the same. Now for C, this one's called shearing flow. So our vector field is f of xy equals y times I. And again, I'll give you a picture of what this looks like. So that's this diagram here. So as we move away from the x-axis, either in the positive direction or the negative direction, then the magnitude of the velocity of the fluid is going to get stronger, but in different directions. So if we go in the negative y direction off of the x-axis, then our velocity is going in the negative x direction. But if we go to the positive y direction off of the x-axis, then our velocity is going in the positive x direction. And this is why it's described as shearing flow, because you can think about the water almost tearing at that x-axis there. So in this case, the partial derivative of n with respect to x minus the partial derivative of m with respect to y is just going to be -1. And so again, the circulation density at all of the points is going to be constant, and the circulation is clockwise at every point in this case. So because our circulation density is negative, then the circulation around the different points is going to be clockwise as opposed to counterclockwise. And this makes sense if you think about taking a water wheel and putting it so that the center of the water wheel is on the x-axis. So maybe it looks something like this with the wheels going out to the side on the x-axis. Then the current or the flow of the fluid here, or I guess in this case it's gas, is going to be pushing our water wheel so that it's rotating in this direction. And that's what the circulation density being negative tells us. And then finally, for our last vector field, we have what's called the whirlpool effect, and it's modeled by the vector field f of xy is equal to -y over x squared plus y squared I plus x over x squared plus y squared j. And in this case, the partial derivative of n with respect to x minus the partial derivative of m with respect to y is ultimately going to equal 0. And if you want to, you can stop the video and just verify that the partial derivatives that I calculated are correct, but the answer is in fact 0 in this case. So the circulation is 0, but it's important to notice that our vector field is not defined at the origin, because once I show you the picture, it's going to look like there should certainly be some positive circulation density at the origin, so right here, because the fluid is certainly flowing around that center there, hence the name, the whirlpool effect. But the circulation density isn't defined at the origin, which is why the circulation density will be 0 everywhere else. So everywhere other than the origin, the circulation density will be 0, and our vector field f is actually not defined at the origin, which is the point around which the fluid is flowing. Okay, so that's the end of the example for circulation density, and then we can move on to divergence or flux density. So again, let f of xy equal m of xyi plus n of xyj be the velocity vector field for some fluid in the plane over some domain R, and let xy be some point inside of the region R. It can be any point, it's arbitrary, and let A be a rectangle that's contained in R. So it's completely contained in R, just like in our derivation of circulation density, with one of the corners at xy. So we have the same picture that we had for circulation density, but this time we are going to look at how quickly fluid is leaving A, as opposed to the circulation rate around the boundary of A. So we're focusing on flux now, as opposed to flow and circulation. So we look at the rate at which the fluid leaves across each of the edges of A, and then just like we did for circulation density, we can sum all of these rates together to approximate the total net rate that fluid is leaving the region A across the boundary of A. Okay, so again, we have our flow rates for the top, bottom, right, and left sides of our rectangle A here. So the top is going to be approximated by f of x, y plus delta y, dot j times delta x. So in this case, we are looking at this point up here, just like we did for circulation density, and we're getting the velocity vector at that point by plugging it into our vector field f, and then we're taking the dot product with j, because we want to know the scalar component of that velocity vector in the positive y direction, because that'll give us how much fluid is actually leaving out of that upper boundary there. And we multiply by delta x because that's the length of the top boundary. And ultimately, this is just equal to n of x, y plus delta y times delta x. So again, this is an expression approximating the flow rate for our top boundary here of our rectangle. And the bottom flow rate and the right and left flow rate will be similar. So for the bottom flow rate, we have f of xy dot minus j times delta x. And this time we're looking at the actual point xy, and we take the dot product with minus j because we want to know the scalar component of the velocity function at xy in the negative y direction. So we're only worried about the fluid that's actually directly in the direction leaving that bottom barrier of our rectangle A. So that's why we dot product with minus j, and then we multiply by delta x again because that's the length of the bottom side of our rectangle. And this will give us minus n of xy times delta x. And then the processes for the right and left side are very similar, so I won't even give the geometric reasoning for why this expression is correct. But the right side can be approximated by f of x plus delta xy dot I times delta y, which is just equal to m of x plus delta xy times delta y. And again, the reasoning for this is very similar. So if you want to, you could even look at the notes that I've posted on Blackboard and just verify that this expression makes sense to you. And then for the left side, we have f of xy dot minus I times delta y, which is equal to minus m of xy times delta y. So with these expressions, we can now take the sum of all of them to approximate the net flow rate of how much fluid is actually leaving the region A across the boundary of A. But we start out just like we did with circulation density by taking the sums of opposite sides. So we take the sum of the rate for the top and the rate for the bottom, and we get n of x, y plus delta y minus n of xy all times delta x. And again, this should look familiar. So this would be the numerator of the difference quotient that we use for the partial derivative. So that's where this partial n with respect to y is coming from. But we multiply by delta y because typically we would have delta y in the denominator. So we have a delta y that's showing up here. And then the delta x is still just carrying over, just like it did for circulation density. And then we can take the sum of the right and left sides, and we get m of x plus delta xy minus m of xy. And then we multiply by delta y. So again, this is the sum of these two now. And the same reasoning applies here. So this looks like the numerator of the partial derivative of m with respect to x. but we would typically have a delta y in the denominator. So this is approximately the partial derivative of m with respect to x times delta y, and then we have, or times delta x, I should say, and then we have a delta y that's also being carried over. And when we sum all four of our boundaries together, we get an approximation for the total flux across the boundary of A. So it will be approximately the partial derivative of m with respect to x plus the partial derivative of n with respect to y multiplied by delta x delta y. And if we divide by the area of A, then we approximate the total flux per unit area, or the flux density of A. So this is kind of the intuitive definition of flux density. So the flux density will then be approximated as the flux across the boundary of A divided by the total area of A, which is approximately the partial derivative of m with respect to x plus the partial derivative of n with respect to y, because the area of A is equal to delta x times delta y. So when we divide, we're just left with this partial derivative of m with respect to x plus the partial derivative of n with respect to y. And if we take the limit of this expression as delta x and delta y go to 0, so as the area of A goes to 0, we find the flux density at the particular point xy inside of the region. And we call the flux density the divergence of the vector field F, which is denoted div F. And here's our formal definition. So the divergence or flux density of a vector field F equals mi plus nj at the point xy is, and then it's given by this div F, equals the partial derivative of m with respect to x evaluated at the point xy plus the partial derivative of n with respect to y evaluated at the point xy. And intuitively, the divergence of our vector field tells us how much a gas is expanding or compressing at a point. So if you pick one point in the plane like this, and then our vector field looks like it's expanding outward from that point, then the divergence of F at that point is going to be greater than 0. And if at our point it looks like the gas is compressing towards the point in the region around the point, then the divergence of F at that point is going to be less than 0. And this leads us to our last example for this first video. So we want to find the divergence and interpret its meaning for each of the vector fields from the first example. So I'm just going to list each of those vector fields as we go through, and we'll calculate the divergence and then interpret the divergence. What does it actually mean? So for the first vector field, we had F equals C times xi plus cyj, and then divergence of F is going to equal the partial derivative of m with respect to x plus the partial derivative of n with respect to y, and we get C plus C, which is just equal to 2 times C. So if C is greater than 0, then the gas will be expanding uniformly. So at every point, the gas is going to be expanding outward from that point. And if C is less than 0, then the gas is going to be compressing uniformly. So I think when I introduced this vector field in the previous example, I said when C is greater than 1, then it will be expanding, and when it's less than 1, it will be compressing, but that's not true. That was a mistake. If C is greater than 0, then the gas is expanding uniformly, and if C is less than 0, then the gas is compressing uniformly. Hence why we called it universal expansion or compression, I think, when it was introduced. For the second vector field, we had F equals minus Cyi plus Cxj. I think this one was called uniform rotation. So everything is rotating about the origin. And in that case, we had that the circulation density at every point was constant. But if we take the divergence of F by taking the partial derivative of m with respect to x and then adding the partial derivative of n with respect to y, we get 0. in this case. So the gas is actually not expanding or compressing at any point. Now if we have F equals yi, so I think this was the shear vector field, then the divergence of F is going to equal, again, the partial derivatives added together, and we get 0. So the gas is, again, not expanding or compressing at any point. And finally, we had the whirlpool effect. So F is equal to minus y over x squared plus y squared I plus x over x squared plus y squared j. And this one looked like a point that was centered at the origin, and then we had some vectors that were going around the point in this direction. But as we got further away from the point, the magnitude of the velocity kept getting smaller. And again, this is called the whirlpool effect. And if we take the divergence, we get 2xy over x squared plus y squared squared minus 2xy over x squared plus y squared squared, so that the divergence is just 0. In this case, again, meaning that the gas is not expanding or compressing at any of the points inside of the plane here. And it's an interesting fact that if the flow of a fluid inside of the plane can be modeled with a vector field such that the divergence is 0 at all of the points, then we would say that that fluid is incompressible, meaning that the fluid doesn't get more dense or less dense over time as the fluid is flowing. So each of these vector fields in B, C, and D, these would be typical models of how you would model the flow of fluids like water, but we would not model the flow of water with A because it would require A to compress or expand at different points, and water does not do that. So that's just an interesting note. And that's the end of the material for the first half of section 16.4. The second half of section 16.4 will deal with Green's theorem.